Okay, this video is here to remind you of something that's almost too simple, but it's worth being clear about. And that is that forces cause accelerations, so that any given force, any given net force, has to be pointing in the same direction as the acceleration that it's causing. Okay, so the net force and the acceleration object are always in the same direction, right? And so let's do an example to flesh this out. If you guys could go to the slide that says pro tip, the net force and acceleration of an object are always in the same direction. Okay, in this problem, there's my bald head, okay, and there's something like this, and then my mouth, right, and then I got a little bit of beard action here, right, and it appears to be that there is a 4.7 Newton force here, right? And there is a 5 Newton force in this direction, right? And these forces are the result of some bullies, okay? It says 2 high school bullies are pushing Scott's 7.2 kilogram head. The one is, due east, and the other one is 45 degrees north of west. So if this is west, right, then this degree here would be 43. Okay, so the question is, what is the magnitude and the direction of the acceleration of my head, right? Very, very important physics question. Definitely we need to know this, okay? So what do? What is the first step anytime we're solving a force problem? Well, we draw a free body diagram. Have we done that? Yes. Notice I'm ignoring gravity, and I'm ignoring the force of the neck on the head. We're not going to worry about that right now. It's just the bullies acting on my head, okay? And so once we have our free body diagram, which we do, we can start drawing our Newton's second law, right? Equations. So we do that. This is definitely a two-dimensional problem because this guy's pointing in two directions, right? He's got a y component, right? So there's going to be a y component here of this guy, and there's going to be an x component here of this guy, right? And this y component has to be 5. This is the component that doesn't touch the angle, so that's going to be 5 sine of 43, okay? And this component here, the x component, does touch the angle, so that's going to be 5 cos 43, okay? So what do? We say that sum of forces in x must equal to max, right? And the sum of the forces in y must equal to may, right? And I actually want to find ax and ay, right? I'm trying to find the acceleration of my head, right? So in other words, ax is just going to be the sum of the forces in x, or my net force in x, over m, and ay is just going to be the sum of the forces in y over m. Okay? Well, what's the sum of my forces in the x direction? Well, I have 4.7 going this way, right? So that's going to be equals 4.7. Then I got 5 cosine of 43 this way. So minus 5 cosine of 43. And all over, I've said that my head weighs 7.2 kilograms. I weighed it before this lecture, right? So this gives me an ax component of, I get 0.14 meters per second squared. Okay? All right. Awesomeness. So now, what's going on in the y direction, right? Well, I only have one y component, right? And that's going to be 5 sine of 43 over the mass of my head again, which is 7.2. And for this guy, I get an ay component of 0.47 meters per second squared. Cool. So I have ay equals 0.47 meters per second squared. Now, here's the deal. I have an acceleration vector, right? My acceleration is just axi plus ayj, right? So the acceleration vector of my head is just going to be 0.14i plus 0.47j. In other words, my head's going to accelerate somewhere in that direction. And we're going to find out what that direction is in a second here, okay? All right, so is this what we're looking for? No, we're looking for the magnitude. How do you get magnitude if you have the components? Well, quite easy, my friends. You just say square root of ax squared plus ay squared, right? Now all I got to do is I got to put my ax in for that, got to put my ay in for that, and I get a magnitude of 0.49 meters per second squared. I just put that into my little Pythagorean relationship over here, right? So now I have this guy over here, okay? All right, now the next question is, what is the direction, right? You guys by now know that to find the direction, theta is just equal to the tan inverse of the y component over the x component. True story? True story, all right? In this case, the y component is just 0.47, so it's tan inverse of 0.47 divided by 0.14, right? And so I get an angle of 73 degrees, right? So in other words, this net acceleration of my head, which is the same direction as the net force, is going to be somewhere up here where this angle here is 73 degrees. Okay. Obviously, this is a silly example. I was just trying to be silly, a little bit entertaining with this whole bully situation. But the bottom line is acceleration can be found just as easily as forces from this Newton's second law analysis, and you can get the components for the acceleration by doing Newton's second law in the x dimension and in the y dimension, right? You can find the actual acceleration vector by taking the ax and the ay component. You can find the magnitude of a by doing your Pythagorean theorem with the two components, and you can find the direction by doing your inverse tan. Okay? So everything you can do with forces, with the force vector, you could also do with the acceleration vector. That's what I wanted to prove with this slide, and I hope I've proved it.